everybody, welcome back. Miss Lakin here at the Putnam Museum and Science Center. I'm excited to be with you here today. We are in the Putnam Space Gallery. Today's topic is all about space. Miss Chris will show you some cool artifacts we have here at the museum. I'll walk you through your activities in your activity kit, and we're going to do a little peek at one of the interactives here in the gallery. So this is the Putnam's Magic Planet. It's a 3D virtual reality sphere, and it's really cool because we can explore our different planets we have in our solar system. So right now, this is Mercury. I'll walk you through and show you some of the different planets. This one's Venus. Oh yeah, this one's really cool. Here we go. We're gonna go to planet Earth, that third planet from the sun. We have Mars, Jupiter. We're getting to our big planets. Saturn, Uranus, and last one, Neptune. So, and we'll actually, I'll show you the sun too, because all of our planets in our solar system orbit and circle around the sun. And then we'll go back to planet Earth. This interactive is really neat too because you can explore and read more about what NASA has developed over time. Some of the things that they have done have made space travel easier and safer. So that's really cool. So with that being said, let's get started.
Hi everyone. My name's Chris Chandler. I'm the Curator of Natural Science here at the Putnam, and today we're going to talk about visitors from outer space, and it's not the ET kind. We're going to talk about rocks that come from outer space. One of the things that's fun about being a curator is you get to deal with all sorts of different types of objects, everything from rocks to fossils to pinned insects and pressed plants. But one of my favorite things are actually meteorites. They actually come from outer space, which is cool. If you're a geologist, you learn about the Earth, and you also learn about everything that hits the Earth, so we get to study meteorites too. Just some terminology, because that makes it really a lot easier for people to understand. I know I always get confused when people start talking about meteors, meteorites, and asteroids. So starting with asteroids, those are great big rocky pieces, objects that are basically orbiting the sun. There's an orbit that goes between Mars and Jupiter, and basically that's where you find a lot of asteroids. They're great big rocky pieces that formed about the same time that the solar system formed. So their size is large. You're talking about things that can be up to like 300 miles across, down to things that are like 33 feet across. That's still pretty big. If you think about 33 feet across, is about the size of somebody's house. That's pretty large. You might never heard the term meteoroid. Not meteor, not meteorite, meteoroid. Meteoroid refers to basically smaller bits of rock that are floating around in space. Talking about everything from the size of dust up into the size of smaller asteroids. The term meteor actually refers to when a meteoroid, or an asteroid possibly, I suppose you could call it a meteor, hits the atmosphere of the Earth or some other planet, and it starts leaving that trail that you can see. You see that lovely trail as it streaks across the sky. Falling shooting stars are meteors. It's not considered a meteorite until it hits the ground. When it hits the ground and produces things like these, then it's actually a meteorite. The meteorite is the actual physical evidence that you have that you can hold in your hand. So that's the simple terms. The other thing you might want to know is that there are a bunch of different types of meteorites. So there are actually three types that we normally talk about. The first would be stonies, stones. You have irons, stones, and stony irons. Can you guess what that last one is? Yeah, it's a mixture of both. Stones are the most common type, and they're basically made up of the same stuff that the rocks on Earth are made up of. So they're really hard to identify. Even though they're probably the most common, you don't have them identified often because you literally have to take them in and have them tested because they pretty much look like a regular rock. If you get one really early after it's landed on Earth, sometimes it'll have what's called a fusion crust, which means it gets dark and burnt on the outside. It looks a little bit like a briquette. But the problem is that's a really fragile crust and it disappears really quickly. So once again, you're going to end up with something that looks like a rock as opposed to something that you think of as a meteorite, which is probably more likely to be an iron. And irons are really cool. This is a piece of a really cool iron meteorite. Now, most meteorites are actually quite small, so this probably was a chunk from a small meteorite. Iron meteorites are a combination of alloy made of iron and nickel. They have a really high nickel content compared to most rocks you find on Earth. So that's one of the giveaways that might be something from off of the Earth, is that it actually has a high nickel content. What you get is this really cool pattern, and we'll get a close-up of this for you that you can see, is called the Wiebenstatten pattern. And it's like this really weird cross-hatching that you see when you see those, and you know immediately when you see that you're dealing with a meteorite. A couple other things that are interesting about irons is that they're really, really heavy. Lots of iron, lots of nickel, those are both really heavy elements. So something like this weighs about 22 pounds. One about the size of your hand would weigh 5 or 6 pounds. That's really heavy for an object from Earth. Stony irons are kind of an interesting thing because they're a mix. So they have both the stony element and the iron element, and I have one that's a halloysite here. Notice that it's got different colors. The darker color inside is actually the mineral olivine, which on Earth, it comes from really deep inside the Earth's crust, whereas you find these on, when they hit the ground with them. And the metal, again, is the nickel iron, so it's a mixture of both. So one of the fun things I get to do, and sort of depressing things I get to do for people, is to tell them whether or not they have a meteorite. Like I said, most meteorites are small. A lot of them are magnetic, so if I were to do that, yeah, magnetic, this one, magnetic. Even the stony iron is magnetic. Most are going to have a lot of iron and nickel in them, so they'll be magnetic, but unfortunately, some that come from the moon and some that comes from Mars, they're not magnetic. So it's not always the dead giveaway if it's magnetic. Other things you can look for is, if you see air holes in your specimen, it's not going to be a meteorite, because as it comes through the Earth's atmosphere, it literally melts, so you're not going to get air holes. If you see air holes like you find in something like this, it's not a meteorite. This is actually a piece of scoria. It's a piece of basalt. One of the things that a lot of people bring in that have air holes are different types of slag. And slag is a product from when you're actually melting different types of metals and doing industrial work. You end up with what's called slag. And a lot of people bring them in. They look really interesting, but they're not meteorites. Some of them are very heavy, some of them are light. They look like they should be something from out of this world, but they're not. They're actually stuff that's produced by industry when you're actually smelting. This is really heavy. It is really heavy. Probably weighs almost 10 pounds. This is actually a piece of iron ore, but it's a hematite. It's not magnetic. It's iron ore, not magnetic. Not a meteorite. This is another piece that is actually kind of cool because people are, oh, it's got shiny bits and it's got dark bits and it's got other bits. It's another piece of hematite. Once again, it's barely magnetic. Hardly feel anything when you do that. And then one of my favorites is, this came in years ago, and it's got a burn crust. And the people were certain that it was meteorite. There's a long story about how it was obtained, and the people had written it down and that it was a meteorite. But basically, it's a piece of granite that's been tossed in the fire and ends up with a burn crust. So it's what we call a meteor wrong. We like to call these guys meteor wrongs.
Hey everybody, Miss Lakin here at the Putnam. I'm excited to be with you today. We're gonna do our space activities. So if you do have your learning kit, go ahead and grab that. I'm gonna walk you through the two that we're doing today. So for the first activity, go ahead and grab out your booklet. You have your activity card in there. The first activity we're gonna do is the Earth, Moon, and Sun paper model. And for that, you'll need, gather your, there's 3 little brads, little metal brads in your bag. You'll need the thinner paper plate, and then you'll also need the template. So go ahead and grab these out. You'll also need to grab some crayons from your kit. So go ahead and grab your box of crayons. Along with these things in your kit, at home, grab some scissors and grab a pencil. And then we'll get started making our paper model. Okay, now that we have all of our supplies ready, we're ready to make the Earth, Moon, and Sun model. So I've done this ahead of time, so you can go ahead and do this. I've colored my paper plate to represent the sun, and I've cut out my template pieces. Go ahead and pause the video and go ahead and cut that out, or just follow along as I show you how to assemble it. Once you have everything cut out, go ahead and you're gonna poke a hole through planet Earth, through the moon, on both sides of your strips of paper, and right in the middle of your sun. And now we're ready to assemble. So go ahead and take your moon, and you're gonna take one of the little brads and go ahead and push that through the center of your moon, and we're gonna attach it to our small strip of paper. So go ahead and push that through and fold down the other side of the brad. So your moon should be attached just like that. Now you're gonna take your planet Earth, go ahead and push the next brad through, and you're gonna attach that to the other end of that strip of paper. And don't close it quite yet. We're gonna add this long piece right here on this side. And then go ahead and close that brad. And the last part to our model is attaching this long end to the back of our sun. So go ahead, oops, the last brad here, push it through the center, flip it over, and attach this long strip to this one. Okay, and here we have our sun, earth, and moon model. And this is really cool. You can demonstrate the phases of the moon by using your moon phase chart. If you want to do that, go ahead and color half of your moon a dark color. And this is the side that is away from the sun. So the sun reflects light off the moon, and that's how one side is light and one side is dark. So let's see, I'll demonstrate one of the phases here. How about the full moon? So here's Earth, here's our sun, and our full moon would be in this position right here. So go ahead, experiment with the different phases of the moon and test out your model.
Canyon Diablo meteorite we have in the museum. It's one of our treasures. We actually have, this guy is actually, from Canyon Diablo in Arizona. It's a big hunk of meteorite, weighs about 22 pounds. Quite amazing that it weighs that much. The Canyon Diablo meteor fell about 50,000 years ago. It made a crater that was about 600 feet deep and about, I think it was 4,000 feet in diameter. So that's a big crater. I mean, it's meteor crater, you know, you look at it and go, wow, that's a meteor crater. The thing that happened with it is most of it exploded on impact and it blew it all over. And so there's fragments everywhere. And this is actually a fairly large fragment. There's thousands of fragments of this thing. The biggest weigh over 1,000 pounds. Most of them average a lot smaller than that. And like I said, this one's about 22 pounds. The cool thing about Canyon Diablo is that they used these meteorites to actually confirm the age of the Earth. They used radiometric dating, which basically is looking at how one element decays into another. And you can time that and know how much time has gone between when you look at the different amounts of each element. And they use that to determine that the Earth is between 4.5 and 4.6 billion years old. So it's really cool that you could do that with meteorites. The other thing I thought we might look at, and the reason there's a map and no, no actual meteorite to look at, is because in Iowa we actually have a very large impact structure. We don't have any meteorites because it blew up before it hit the ground and it literally disintegrated into, I guess, dust is what it would end up being, if that. It pretty much vaporized on impact. This happened about 74 million years ago. That's during the age of the dinosaurs. That's late Cretaceous. And it happened near Manson, Iowa. Around Manson, they always thought something weird was going on with the geology there. Around Manson, they actually had soft water. They also dug wells and they would find what looks like breccia, which looks like rocks where you've basically thrown them down and broken them into pieces and they're all jumbled together and they have sharp edges. That's not common for around here. And finally, when they were drilling cores, they actually drilled cores down in to see what's going on, they came up with that they had found shock quartz. And quartz actually will change if it's impacted really, really hard. You actually can change the structure of quartz. and they found shark horns. And they're like, okay, that means something really weird has happened here. And at first, they thought maybe it was a volcano, that maybe it was a volcano that was under the ground. Well, when they started looking closer, they realized it's an impact. It's a huge impact crater. So like I said, the problem, of course, is that it's covered by all the sediment that's from glaciers that have come down. So it's covered by like 100 to 300 feet of glacial drift, which means it's really hard to study it. But what they figured out now is that it's like 23 miles across. The object was probably about a mile in diameter. It may have weighed up to 10 billion tons, and it probably hit the Earth at a speed of about 45,000 miles per hour. Obviously, that's why it basically vaporized when it hit. So some of the things, we always talk about what happens when one of these hits. Probably set fire to everything within 130 miles of the impact, which is pretty much all of Iowa. Would have been toast. May have, because it hit at the edge. This is where this is actually at the edge of what would have been a Cretaceous seaway, a very shallow seaway. Could have easily created a huge tsunami, giant tidal wave. Also would have spewed a bunch of carbon dioxide and water vapor into the air. Not good either. The shock wave that it produced probably would have toppled trees up to 300 miles away. So we're talking toppling trees from Chicago to Minneapolis to St. Louis. And the real sad part is within about 650 miles in radius around it, probably killed every animal on that space between. So that's like from Detroit to Denver. Pretty much all the dinosaurs would have died. Dinosaurs have had it a hard time, right? I mean, you gotta feel sorry for them. One of the things that's one of those things where it's like, if you think about what would have happened if they hadn't had the asteroid impact. Because at one point they thought that this one might have been the dinosaur killer. But they realized that it actually was too early. It's about 9 million years too early. Dinosaurs had 9 million years to come over and take the land over again in the area, because then about 9 million years later, down at the tip of the Yucatan Peninsula, another huge asteroid hit, and it probably was about 5 times the size of the Manson impact. And we all think those are really huge, and it is terrible because if you think about it, it killed about 50% of all animal life on the planet, actually possibly 50% of all life on the planet. But that's not the worst one, right? Before the age of the dinosaurs, at the end of the Permian, there was one that possibly was an asteroid hit also, and it killed up to 90% of all life on the planet. That's just crazy. The good news is that they only happen really, 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 really rarely.
Okay, so we have all of our supplies ready for the second activity that has to do with space. So this is the Sundial activity. You're gonna need your hard paper plate in your bag, clear straw, and 2 rubber bands. And also grab your paper ruler out of your kit, and you'll need a pencil. So go ahead and grab a pencil. So for our sundial, the first thing you're gonna do is take your paper plate and you're gonna poke a hole right through the middle. So go ahead and poke your hole right through the middle. I'm gonna make that a little bit bigger because our straw is gonna go through that hole. And we're gonna take our ruler, and from the center, from that hole that you just created to the edge, you're gonna make a straight line, or just make a line using your ruler on one side. And that's gonna be the start of our sundial, our sun clock. And I'm gonna put 12, and that's gonna be for noon. Then you're gonna take your clear straw, go ahead and poke it through the center hole that you created, and you're gonna use your rubber bands to secure your straw in place. So go ahead and wrap those rubber bands, wrap that rubber band around that straw. And this one's being a little tricky. Okay, I'm just gonna push that through. Oop, there we go. And I'm gonna do one more. I'm gonna use my second rubber band, and I'm gonna twist that right on the edge, just like that other one. And that's gonna help secure our straw in our sundial. So that's the beginning of your sundial. Now we're ready to experiment and see how it works. So we're gonna take this outside, and the sun, we're gonna see how shadow and the sun play a part in making our our solar clock work. Okay, we have our sundial and now we are ready to see how it works. So go outside, find a nice sunny spot. I'm just right outside the museum right now, and set your sundial down. And the first thing you need to do to set it up is look for where the sun is and where the shadow is on what the shadow is casting from your straw on your plate. So, it looks like it's getting a little brighter out right now. So right here is my line that I drew with the 12 on there. I'm gonna line my shadow, or the shadow, in my lineup. So to do that, go ahead and just twist your sundial around until the straw shadow matches the line that you drew. And it is kind of windy out here today, so I'm gonna place some rocks on my sundial just to be safe that it doesn't blow away. So once your shadow, or the shadow and the line are matching, then I want you to do a little prediction. So guess where the shadow is gonna be in roughly 1 hour. So right now, it is exactly noon here. So I'm gonna come out at 1 and see if my shadow has moved. So think about where you think it might be. Will it be in the same spot? Will it be a little farther away? So just make your guess. And if you want, I even have a pencil. Maybe I'll even mark. I'm gonna guess that maybe the shadow is gonna be right here in 1 hour. And if you start this not at noon, that's fine. You can start it at 12:15. And you can come back at 1:15, so just an hour later, and see what how it's changed. Okay, welcome back. It has been an hour. Let's see. It is 1:01, so we're very close to our hour mark. And it looks like our shadow has definitely moved. Okay, so to record our results, I'm gonna use my ruler, and you're gonna need a pencil. And I'm gonna mark where the shadow is cast, and I'm gonna use my ruler to draw my second line. So if you can see that shadow, go ahead and mark your first line. So I'm gonna put a 1 by that mark. And actually, it was really close to my prediction there. Really close. Oh yeah, look at that. The sun's coming out, so that's how you can really see it. Okay, so go ahead and continue on every hour to see how your mark gets close to where you predicted it was going to be, and see if you were close. So continue doing this. So this was our first hour, so go ahead and you can do a couple more hours. And then if you want, you can even you can do it tomorrow and continue on with your sundial. So just make sure when you do it to place your sundial in the same direction as you did it today while we were doing it. So really cool. So have fun experimenting and making your predictions, checking and marking, and see how your sundial turns out at the very, very end. Okay, we are back in the museum. I am standing in the Putnam Space Gallery, and let's check out how my sundial turned out. So how did yours turn out? Were your predictions close to what you thought where the shadow was gonna be? So here is where the shadow was cast at noon when we started. And look, it moved all the way over here. Just like on a clock, when it moves from hour to hour, our shadow also moved the same way. So this is how we have our sundial, our sun clock. So I hope you had fun doing your activities and learning more about space, and we hope to see you on the next one all about weather.